All right, so when an object absorbs any form of radiant energy, this will result in an increase of molecular motion, and hence it will result in an increase in the temperature of that object. Because all of the objects absorb some sort of energy, all of the objects will also emit some type of radiant energy as well, regardless of their temperature. Okay? So hotter objects, however, will actually emit more radiant energy per unit area. And the hotter that the object is, the shorter that the wavelength of maximum radiation is as well. So, for example, the sun, which has a surface temperature of 5,700 degrees Celsius, radiates a maximum energy at 0.5 micrometers, which, as you can see in the image, is within the visible light range. So this is 1 micrometers, this is 0.001, so that's going to lie somewhere around here in the visible light range. So as a contrast to this, the Earth, which has a much cooler surface than the Sun, has a maximum radiation of 10 micrometers, which, as you can see, is going to lie, where is this milliliter? So it's going to lie around here somewhere. So a lot further in terms of the wavelength, a much greater wavelength of radiation. So typically, the Sun is said to have short-wave radiation, and the Earth is said to have long-wave radiation. Okay, so again, warmer objects are going to have shorter wavelengths and are going to be hotter, and then cooler objects are going to have longer wavelength for radiation and hence cooler. So another aspect to make clear is that the objects that are good absorbers are also good emitters. So both the Sun and the Earth are almost perfect radiators because they absorb and emit with about 100% efficiency for their respective temperatures. Opposed to the Sun and the Earth, for example, gases are actually selective absorbers and emitters. They will absorb, or they will only absorb and emit certain radiated wavelengths, as we'll see in a bit, and that's going to have an effect on the warming and the cooling of the surface or the areas that are surrounding these gases. Okay, so the figure to the left of this slide shows the paths taken by the incoming solar radiation, which have been averaged throughout the Earth. So this is an average of all the paths that have been taken. So here you can notice that the atmosphere is basically transparent to the incoming solar radiation. About 50% of the incoming radiation is actually absorbed by the land and the sea surfaces. Another 20% is absorbed by the atmospheric gases and the clouds. And then the remaining 30% is reflected back to space. And this reflection occurs from either the surface, and we'll talk about this in a bit, from the clouds, and from other atmospheric gases. So this property, which is the total radiation that can be reflected by a surface, is called the albedo. So the image on the right shows a few different surfaces and the amount of radiation that is typically reflected by them. So the albedo for Earth as a whole is thus 30%, again, which accounts by the reflected radiation by the land surface, by the clouds, and by the atmosphere. The factors that are going to determine whether the solar radiation will be transmitted to the surface, whether it will be scattered, or whether it will be reflected outward, depend greatly on the wavelength of the energy that is being transmitted. And they will also depend on the nature of the intervening material. So for example, if the sky is overcast, then more of the energy is actually reflected back to space than if the sky is clear, because there's a greater cloud cover, and hence there is greater reflectance, there's a greater shield, there's a greater albedo than if the sky is clear. So in the image here on the right, again, you see the different surfaces and their albedo. So for example, lighter colors for the most part are going to have a greater albedo than will the darker colors. So as you're seeing, snow has a 50 to 90% effect, and then asphalt, which is much darker, or a darker roof, are going to have 5 to 15%, so much darker, or much lower. So if the Earth had no atmosphere, it would actually experience an average surface temperature that would be far below freezing. But thankfully, this is not the case. So the role of the atmosphere to heat the Earth's surface has actually been named the greenhouse effect. Okay, so as I said before, much of the incoming shortwave radiation from the sun is transmitted to the Earth's surface without much of a barrier. Only a small amount is absorbed through some sort of particles within the atmosphere, some sort of the gases or some aerosols. So this does not happen with the outgoing long-wave radiation from the Earth back to space, however. Much of this emitted radiation is absorbed by the water vapor or the carbon dioxide or any of the other trace gases that are within the atmosphere. And because the energy that would have been radiated back to space is now absorbed within that kind of lower area of the atmosphere, this ends up heating the Earth's atmosphere, and the energy will also be re-radiated back to the Earth's surface, as you're kind of seeing that it occurs right here. So these are three different scenarios. One of them is from the moon, where there's no atmosphere at all, as you're seeing everything that is incoming shortwave solar radiation is exiting as long-wave, I guess, lunar radiation. In the Earth, we have some incoming shortwave solar radiation, some outgoing long-wave Earth radiation, but some of this gets trapped or gets absorbed by the gases, the greenhouse gases, and it gets re-radiated back to our surface. This case of Venus, where the greenhouse gases are so great, explains why Venus is so hot and so toxic, because the amount of greenhouse gases is basically capable of absorbing all of the outgoing long-wave radiation from Venus and trapping it in the atmosphere of the planet. So this effect was termed the greenhouse effect because it acts similarly to how greenhouses are heated. So as you can see here in the image on the top right, the energy from the shortwave radiation from the sun is going to heat up the greenhouse, and part of the long-wave radiation cannot pass through the glass and gets re-radiated back inside. So shortwave radiation, long-wave radiation, some of it does exit, but some of it gets re-radiated back inside of the greenhouse itself. So in truth, much of the heating of greenhouses actually happens because the air is really not allowed to mix with any of the cooler air outside of that enclosed area. But still the term greenhouse effect remains, so we keep it. So many different hypotheses have been proposed in order to explain climate change. Some of them are controversial, some of them have gained support, then lost it, and then gained it back. But overall, this is a very hard phenomenon to explain, as atmospheric processes really occur at such a large scale, and they cannot be reproduced physically in a laboratory setting altogether. Some of the processes can be, but not all of them together. And these processes must be modeled, or they must be simulated on these massive computers in order for us to kind of get a perspective of how they will act. And if you've ever taken any beginner's modeling course, the first thing that you learn is that there is no model that is perfect, and they will all have some mistakes. Some assumptions have to be made in order to make them, and some of these assumptions may be wrong. So now we're going to go ahead and examine a few of these hypotheses that have been made for climate change. And these have, for the most part, earned serious consideration from the scientific community. So these hypotheses will describe the natural causes to climate change, or in other words, the causes that are unrelated to human activity. And in a few slides, we'll go ahead and look at the possible causes that explain climate change seen from a human interaction perspective. Okay. As you'll see, there are many hypotheses that may explain the same effect, and that doesn't necessarily mean that one of them is correct and that the other one isn't, but that it could be that they are all kind of contributing to that effect of climate change that we're seeing. So another thing to have in mind as we go through these coming slides is that no single hypothesis can explain the climate changes seen on all of the time scales. Some of the hypotheses may provide explanations to changes in climate change over millions of years. Other hypotheses may only explain the changes that we have seen over hundreds of years, and others over decades, for example. So, for example, you may remember from chapter 15 that there were two main hypotheses explaining the glacial and the interglacial periods. These were the plate tectonics hypothesis in this case, because it was towards explaining the glaciation periods, and the Milankovitch cycles. So these same two hypotheses have an effect on climatic changes and atmospheric heating. So the shifting plates across the globe change the latitudinal exposure to solar radiation. And with this massive mass movement, a change in evaporation and precipitation patterns occur. Also, different changes in the ocean currents, which in turn will carry the heat differently throughout the globe, will be experienced when you have this plate move. But for the plate tectonics hypothesis to have an effect on climate change, typically their effect has to do on a scale of millions of years. So also from chapter 15, again, we saw that the Earth has certain orbital cycles, or rather the Earth's Milankovitch cycles, which were eccentricity, obliquity, and precession. These will have an effect on the seasonal as well as the latitudinal distribution of the solar radiation, but again, they will have an effect on a much smaller time scale, so on the order of years to thousands of years. So here's another one of the hypotheses that is thought to affect part of the climate change. So the idea that volcanic activity actually had an effect on the climatic variability was proposed a very long time ago. And it is indeed regarded as a plausible explanation for some of the aspects of climatic variability. So as we learned in chapter 5, with explosive eruptions, a huge quantity of gases, along with ash and fine-grained debris, are ejected up into the atmosphere. Sometimes some of these particles are ejected high into the atmosphere, many kilometers above the surface. So this material is later spread around the whole globe by the upper wind currents, and there it remains for months or even years. One great example of this hypothesis is a period referred to as the year without summer, which followed the April 1815 eruption of Mount Tambora, which happened in Indonesia. So from this volcanic eruption, a huge column of about 4,000 meters high expelled 100 cubic kilometers of volcanic debris. So the ejected aerosols that had an impact on the climate actually were widespread throughout the globe. In Europe and in North America, for example, in the following summer months, so May, June, July, August, there was a heavy snow, and there were also big frosts during July and August, which is, to say the least, very uncommon.